Hello, good morning, class. How are you today? I hope you all are doing fine because now we are about to study physics with me, Mr. Isan. And please prepare yourself. I don't want to see any textbook from other subject in your desk. Please clean your desk. Just put your physics textbook, the notes, the pen, maybe the calculators, so you all are ready for study. Are you all ready? Okay, then let's start. Let's start with a question. On all eyes, everyone here, all eyes look at me now. I have a question for you. Am I moving? What do you say? Am I moving? Most of you will answer, no sir, you are not moving. And guess what? That is actually correct answer. Because I'm just standing here in front of you. Now, I would like to all do something a bit different. It's called a thought experiment. Doing experiment just in your head. Can we do that? Okay. So, think about this. You are now in the ISS. Yes, the International Space Station. And I'm here on Earth. You are looking at me. I know this is sound weird. How can we look for that far distance? But again, this is just a thought experiment. So just imagine it. Okay? Then I will ask you the same question. For you all out there in the space station, am I moving? What? The answer difference now, I'm in motion, I'm moving. That's actually also correct. Because probably you see that the Earth is rotating, the Earth is orbiting the Sun, you see the difference on our distance. There is the displacement happen. So you can say, I am moving. Okay. Do you see what's the weird things here? Both of questions are asking about me, am I moving or not? I'm stand where I am. Like when I first start the class and when you are in the space station, I'm just stay there. But the situation's different. The first situation you said that I'm not moving. The second situation you said I'm moving. And both are correct. That's called relative. So motion actually is relative. It is not a fixed definition. It depends on your reference. And that will be our topic for today about the section 5 from the unit 1, Galilean and special relativity. But for now, we'll be focusing on introduction to the reference frames and transformations. Hopefully, after these sessions, you all be able to understand about the reference frames, either inertial or non-inertial. And also about the Galilean transformation equations, the position x prime and the tan c prime. And then the last one, the velocity addition equation. Are you all ready? Okay, because you all are ready, let's just start with the first one. Defining the inertial reference frames. What is the inertial reference frames actually? So, it is a frame of reference where Newton's first law, the law of inertia, is valid. What does it mean by that? It means when you are taking something as the reference, that thing must be at stationary or at rest, because the rule is the Newton's first law is valid. Even though the object is moving, if you are taking it as the reference, you assume that it is at stationary or at rest. That's why the characteristics here, it is at stationary, and the second one, it is not accelerating. Because if it's accelerating, it's gonna be the second one, right? And then If this is not applied, it becomes the non-inertial frame. But don't worry, we are not talking about this now. We're just gonna be focusing on this. I will show you example to make you have a better understanding on this one. Take a look at this picture. On the upper picture, you will see there is a boy and a girl. The boy is inside a train and the girl is in the platform, just standing there. And now, the train is moving to the right. How will the girl see the boys? Based on her perspective, if she is taking herself as the reference, she will say that the boy is moving to the right. Because of course there is displacement between them gonna happen. That's correct. But let's take a look at the lower picture. This is the picture from the boy's perspective. What the boys know, he's just there sitting on the couch. And he is taking himself as the reference, as the initial reference. On that note, it means he thinks that the Newton's first law is valid, he is at rest and stationary. And then there is gonna be a displacement between him and the goal. So, from his perspective, instead of him moving, he will say that the girl is moving away from him. Again, both of these are correct because different perspective, different reference. So that is what I meant before. When you are taking something as the reference, think about it as stationary. Just like the boy right here, even though he is inside a moving train, he thinks himself as the stationary because he is taking himself to be the initial reference frame. Got it? Okay, let's see this one. Now, we are talking about the second objective today, about the Galilean position transformations. What is this? It sounds complicated. Actually, it is not that complicated. When we talk about position, most likely we're gonna use the Cartesian coordinate system. Let's say I have a grid right here. I can draw I can treat this as the Cartesian coordinate system, right? I can draw this. This is gonna be my y-axis, and this is gonna be my x-axis. This is the y, this is the x. And then, as the coordinate, let's say I have a block here. I have a dot. What will be the positions of this one? It will be, let's say, in the position of 2, 3. So that's how you use coordinate to tell the position of an object. If in 2 dimension, it's gonna be only the y and the x. Or if you want to make it 3D, you will add another axis here, the z-axis. So that is about the Galilean transformations. It is just about the coordinate. For this one, when we talk the position in space, if it's 3D, we can assume it is in the position of x, the y, and the z. But the Galileo, he had something here, because we are talking about the motion as well. So, other than the space coordinate, he had the extra one, which is the coordinate of time. Galileo not only thinking about the space, the x, y, z, but also about the times. How do we apply it? Let's imagine these situations. Not imagine actually, because you have here the picture. So just look at the picture then. Person C is stationary, whilst person D is moving away from person C at velocity v. Based on this sentence, it seems like in the beginning, this man right here was in the same position as the C, right? And then he is moving. Got it? Okay. He is moving at the x-axis. Does it moving at on y-axis? No, right? It is just going to the right, not moving up or down. So the difference here, it's only happened on x-axis. And then the story continues. Both person C and person D witness a balloon pop at some distance away. Oh, a balloon pop at some distance away. How will the Galilean think about this one? How can the transformation of position happen? This is the catch. Here, the C stands at the origin. So, he stands at the x0, and the y something. The z, can we just ignore it for now because we're not gonna do the 3D. And then it at the time 0. That is the first situations. And then, because the d is moving, the time is no longer 0. So the time will be t. Time will be t. At the time t. Okay. That is from the C perspectives. And then, what about from the person D perspective? After the time t, he is now at the position of x prime. This is his new positions because he is no longer at 0, right? He is already moving. And then, at the y prime, there is no difference with the C perspective. So they say that it's gonna be the same. Okay, so the time for the D is the same with the time for the person C. The difference here, it's about the X. Okay. Now, he said that he's already moving to the position of X prime. Now, the question is, how far is the x prime from this man, the person C? It really helps us because we have the object here, the balloon pole. So, let's calculate it. Let's measure the distance between the person C with the balloon. We can say that the balloon is x meter away from the person C. And then, for the person D, he will say that the balloon is x prime meter away from him. And then, how far is the person C from the D? It will be the velocity of D times time. So in this case, the side of the x prime, it will be equals to the total x minus vt. So that is the position of x prime. And then the changing of this from the xyt only into x prime equals x minus vt, that's what we call as the Galilean transformations. It's changing now. Is it clear? Are you sure? I think it's better for us to have an example for this, to have a better understanding, right? So, a car is moving at v of 20 meters per second. A pedestrian is 100 meters ahead of the car at t0. The frame S here, it means we assume that this is the stationary observer. Where is the pedestrian relative to the car frame S prime at t 2 seconds? Let's sketch these situations. Just like every time we have problem with motions, sketching the situation is a better option. First, we have a car is moving and then we have pedestrian. This is our pedestrian. They're standing at the 0, 0. And then we have a car here. A car approaching him from the distance of 100 meters. And then what would happen, and this is when the time is still 0. This is the diagram. And then we will treat it. Okay, that's what happened here. And then we are doing this. Can we? No. Can we? No. That's okay. Let's just read through it again. Then, when the time t is 2 seconds, the car is no longer here, it is in this position. The question is, how far is the pedestrian from the car now? How far is it? And let's calculate it. So the x prime equals to x minus vt. The x previously is 100 minus vt. This one is the movement of the car, vt. It will be 100 minus, what is that? The v is 20 and the time is 2. You will get 60 meters. That is how the Galilean transformation applied. If this is clear, I'm sure you can answer this one. Okay, read the problem. A train travels through a station at constant velocity of 15 meters per second. One observer is sitting inside the train, and another sits on the platform. As they pass each other, they start their stopwatches and watch a child on the train run at a constant speed in the same direction as the motion of the train. The observer on the train measures the speed of the child to be 2 meters per second. The questions: according to the observer on the train, how far has the child moved after 10 seconds? According to the observer on the platform, how far has the child moved after 10 seconds? Okay, let's answer this together. Or you want to start first? You want to try first? Okay, if you want to try, I will give you 5 minutes. Try to solve it. Okay, now let's just discuss this one. Every time we have problem with motion, the best way to just catch this situation. We have a train here. The board is done. Work with me. Oh my god, what happens with the board? Now, let's do it again. We have a train here. And then we have observer. Let's name it observer A inside the train. And then we have another observer, the observer B. Okay, what else missing? Oh yeah, we have a child here. There's a child running. So at first the child is here. And then, is the train moving? Yeah, the train is moving, right? With a V of 15 meters per second. And then, the child is also running with a V of 2 meters per second. The first question, after 10 seconds, how far is the C from the E? So, just isolate this part inside the train, because the question is focusing what happened inside the train. Inside the train, the A is gonna be the initial frame of reference, because he is the reference. He will treat himself as the stationary. Only the child is moving. It means for the first questions, the kid will be at the distance of Vt from the man. It will be 2 meters times 10 seconds, 20 meters. So the kid is moving. He is gonna be at 20 meters from the man. Probably I can isolate the kid. I hope so. Okay, we cannot isolate it. Oh, sorry, I cannot isolate it. I draw it too close. That's fine. let's gonna erase it. After 10 seconds, the kid's no longer there. It will be here. At a distance of 20 meters. Now, we will do the second questions. The second questions, it is the observation from the B. Of course, since the train is moving, this train right here is moving, it's gonna move away from the observer. Oh, I cannot isolate it again. Okay, I can. It's moving. Oh, the rope is missing. Let's take it back. Move here. The train is moving. It's moving away, and now we have a new distance. The child is not far. It's the distance of x from the observer, and the train is moving away by vt. So, for the formula, based on this diagram, we say that the x equals to the vt plus the distance of the kid from the observer A. So the observer B will say that the kid will be 170 meters away from him. That is how we apply it. Okay, I hope you all understand the concept of the Galilean transformation now. If you understand, it means we can move to the next part. Let's talk about the Galilean velocity addition. So what is this topic about? This part is about how an observer understands the motion of an object. In the example that I put here, I have a stationary observer. I have the man in the moving skateboard that throws a ball. We are talking about the speed of the ball now. Of course, the speed of the ball received by the man as the observer will be different with the man who throws it, because he himself is on the moving skateboard. Let's make an adjustment here. Let's make an agreement. Let's say the speed of the ball that the observer sees from distance is u. Okay? And then this should not be here. This one should not be here. It should be the speed of the skaters. And then this man in the skateboard is moving with the speed of v. He throws a ball. To him, he said that the speed of the ball is v prime. The speed of the ball received by this man will be faster than compared to the man who throws it. And then if you put that into the equations, the speed of the ball by the observer should be the speed of the ball from the thrower with the speed of the thrower itself. You must apply a logic here. Logical thinking is very required to understand this topic, the velocity addition. Why do I say so? Probably this one will help you understand more. Two travelers, X and Y, will pass each other at an airport. Both of them are moving in the same direction. Traveler X walks at 1.5 meters per second, whilst traveler Y walks at 2.1 meters per second. I think we have the diagram that helps us to understand. Calculate the velocity of traveler Y relative to the traveler X. So the X and Y, both of them are moving, right? But Y is faster. It means like the speed of the Y that received by the X is just the difference between them. What will be the difference of speed between the two? So it's gonna be 2.1 minus 1.5. It will be 0.6 meters per second. So the X thinks that this Y is 0.6 meters per second faster than me. That's what we think. And then, what about the Y? How the Y will receive or will understand the speed of the X? The traveler X relative to the traveler Y. Because when we are taking something as the reference, we consider it as the one it's stationary, right? If the Y thinks that she is stationary, he will find out that this guy is also moving away from her backward. But how fast is it moving away? It's gonna be 1.5 minus 2.1 or negative 0.6 meter per second. Negative means it explains about the directions. The person Y would think that the X is moving away backward from her by 0.6 meter per second. Okay, I will give another situations to think to help you understand. Again, the thought experiment. Imagine you are running with your friend, your best friend or anyone. You are running side by side. Like for 20 minutes, you always side by side. According to you, is your friend moving? You always side by side. Of course, you will say that your friend is not moving because he always by your side. He never displaced from you. So there is no velocity if there is no displacement. That's how we understand about the velocity equations. Okay, is that clear? Okay, let's continue the story of these two. Travel X now walks onto a travelator walkway in the airport at the same speed. The travelator moves at 0.3 meters per second, and travel Y decides to take a seat facing the travelator. So now she is just at rest. Calculate the velocity of the X relative to the Y. How the Y sees the X. Because now the X is on the travelator that moves with the speed of 0.3, and he is also there with the speed of 1.5. It means like the speed of the X by the Y will be, the speed it's gonna be the 1.5 plus 0.3, 1.8 meter per second. Okay, because it's gonna be faster, of course. It's not only him moving, but also the travel that helps him move. The next one, the travel X relative to the travel Y when he is walking in the opposite direction to the travelator. Oh, that's interesting. Now, this is the X. It's moving here 1.5, but the travelator is here 0.3. If the same direction is going to be faster, of course, different directions is going to be slower. So, this thing right here, it will be 1.5 plus 0.3. It's going to be 1.2 meter per second. Remember, velocity is vector, so direction matters. That's why here, at first, the same direction, we assume it's positive. Different directions, we will assume it is negative. Okay. How clear? Now let's compile what we have studied with these questions. In deep space, rocket A leaves the space station with a constant velocity of 300 meters per second. At the same time, rocket B travels in the same direction with a constant velocity of 200 meters per second. Calculate the distance between rocket A and the space station after 1 hour. According to an observer in the rocket B, what is the distance to rocket A after 1 hour? In rocket B's reference of frame, determine how fast an observer would measure the speed of rocket. This is gonna be your exit ticket for today. Please answer these questions. I give you a hint. Don't forget, this is meter per second, so it means the time should be converted. And then, yeah, just apply everything that you have learned today. If you're not doing this, you cannot be dismissed from my class. Okay, everyone, that is our topic today. That is the presentation from me. And hopefully you understand. We have studied all of the objectives. Let's revisit them again. It's about the reference frames. Again, if you are taking something as the reference, you must assume that thing is at stationary or at rest. Galilean transformation equations, it is just about the coordinate, and then the velocity addition equations. For these two, just apply logical thinking. It's very gonna be useful. Okay, to give a trigger for you to study for the next part, to end these sessions, not only with the exit ticket, I will give you with this thought experiment. Think about this one. What if the speed of the boy in the skateboard is 0.8 of speed of light, and he throws the ball with a speed of 0.3 speed of light? What do you think the speed of the ball received by the stationary observer? He will think the speed of the ball is 1.1 of speed of light, right? The question, is this possible to have the speed bigger than the speed of light? That will be our discussion for the next meeting. So please be ready and submit your exit ticket. Bye bye everyone.